Good afternoon. My name is Jean-Louis Briot. I'm a distinguished professor at Texas A&M University and the holder of the Spencer J. Buchanan Chair in the Zachary Department of Civil and Environmental Engineering. This year, I'm also past president of the American Society of Civil Engineers. So if you're a member, thank you, and please continue. If you're not yet a member, please become a member. I can assure you it is a very good deal. If you do not think so, please drop me a note so we can have a good visit. And if you're a student member, ASCE has a lot to offer, including financial support. Check the ASCE Foundation website. Welcome to the 29th Buchanan Lecture. Thanks to the contributor to the Buchanan Chair, the Buchanan Lecture continues to be free of charge for all participants. I also want to recognize those who have sponsored graduate student fellowships in geotechnical engineering at Texas A&M University. Todd Swoboda, Patrick Beecher, and the Terracon Fellowship. Willie Bowman, his wife Mildred, and the Bowman Fellowship. Alan Young, who created the Donmer Fellowship. Mark Balus and the Balus Fellowships. ACS with Carl Higgins and Mark Zortman, and the ECS Fellowship. We'd like to continue to raise more funds for fellowships to support our geotechnical graduate students. These funds go a long way to help them. For example, a competitive fellowship of $1,000 allows an international student to get in-state tuition, which lowers their cost by some $6,000 annually. So your $1,000 gift has a seven-fold return and a tremendous impact on their lives. I also want to acknowledge another special group, and that is the board of SURGEP, the Consortium for Education and Research in Geoengineering Practice. This group of companies fund research aimed at solving problems encountered in practice. SURGEP now has 14 member companies, and I want to thank them for their proactive impact on practice-oriented research. The chair of the board is Shailendra Henley with Intertech, and the vice chair is Todd Swoboda with Terracon. Besides Intertech and Terracon, the company's member of SURGEP are A.H. Beck with Tracy Brightman, Aviles Engineering with Wilbur Wang, ECS with Mark Zortman, Fugro with Anwar Akhtar, Geosyntech with Rodolfo Sancio, Kiewit with Ryan Coggins, Ménard with Jonathan Dwight, Paradigm with Ray Meyer, Rabba Kistner with Gary Rabba, Reinforced Earth with David Hutchinson, Reiner Engineering with Ken Reiner, and Tolune Wong with Daniel Wong. If you wish to join SURGEP, please talk to me or Shailendra or any SURGEP member. I also want to recognize Blake Thurman, my assistant, who's helped me to organize this lecture. Now for the program. First of all, this is the second time in a row that we offer the Buchanan Lecture online because of the COVID virus. I hope that next year we'll be back to an in-person lecture event. Note that the Buchanan booklet, including the speaker's PowerPoint slides, will be posted on the Buchanan Lecture website. We're also video recording this event, and we'll post the video on the Buchanan website within the next few days. We'll also give the video to the Geo Institute of ASCE for them to upload on their website, along with the 28 other Buchanan Lecture videos going back to 1993 when Ralph Peck gave the first Buchanan Lecture. Our first speaker will be Dr. Philippe Jean-Jean with BP America in Houston. He will deliver his 2021 Buchanan Lecture, which is about 1 hour. Our second speaker will be Professor Ed Cording from the University of Illinois. He will give the 2020 Terzaghi Lecture, which is also about 1 hour. We will not have any questions in this setting. The event will conclude after his lecture. Now it is my great pleasure to introduce Dr. Philippe Jean-Jean. You know, in 29 years of Buchanan Lecture, we have very rarely selected one of our own. In fact, we've only done this twice. The first time was when we selected Professor Jose Rosette, who gave the 2009 Buchanan Lecture. And the second time is today, when we honor one of our own graduates. Dr. Philippe Jean-Jean graduated from the École Centrale in Lyon, France, in 1989, and from Texas A&M University with a Master of Science in 1991 and a PhD in 1993, both in civil engineering. He began his career with Amoco Petroleum Company in Tulsa, Oklahoma in 1993, and was transferred to Houston, Texas in 1995, where he still works with BP America. He currently is a senior advisor for geotechnical engineering, the highest ranking geotechnical position in the company. Dr. Jean-Jean has 28 years of experience in leading activities such as the planning and execution of onshore and offshore geotechnical site investigation, geohazard assessment, designing and assessing shallow, intermediate, and deep foundation for fixed and floating offshore platforms subject to hurricane or earthquake loads, design of flow lines and pipeline, and geotechnical support for offshore well drilling activities. Dr. Jean-Jean is very invested in many professional committees and activities. In particular, he's a member of the International Society of Soil Mechanics and Geotechnical Engineering and chaired its technical committee on offshore geotechnics from 2009 to 2017. He's been a member of American Petroleum Institute and ISO committees on geotechnical and offshore foundation for 28 years and chaired the API committee from 1999 to 2014. He's also the co-chair of the 4th International Symposium on Frontier and Offshore Geotechniques, which will be held in August 2022. Dr. Jean-Jean has authored and co-authored more than 60 technical articles. He's been a guest speaker or keynote speaker at numerous conferences, delivered the 2019 Coulomb Lecture, and holds a patent on extrapolating geotechnical information using seismic reflection data. In 2015, the United States Board on Geographic Names agreed to name an underwater site in the Gulf of Mexico the Jean-Jean Basin to honor Philippe and his substantial contribution to the advancement of geotechnical and geological knowledge of the seafloor of the Gulf of Mexico. Philippe, on a more personal note, I must tell you that while I'm very proud to have been your PhD advisor, I did not nominate you for this Buchanan Lecture. Someone else did. And of course, I endorse the idea wholeheartedly. I recall our visits in my office when you were a student as we were struggling to solve difficult problems. I also recall reading and correcting maybe a bit overzealously the wonderful dissertation you wrote when the solution became clear. This was the early 1990s, which was also the beginning of the Buchanan Lecture. Some 30 years later, it's my distinct pleasure to give you the floor and ask you to deliver the 2021 Buchanan Lecture entitled Offshore Geotechniques from Oil and Gas to Renewable Energy. Philippe, the floor is yours.
Well, thank you, Dr. Brio, for this very kind introduction. Let me share my screen and let me know if you can see the first slide.
We see it. Yeah, perfect. Go ahead.
Let me try to see, is there any way I can remove this bar at the top?
No, we want to see you.
Okay, good.
Yeah.
Well, thank you. It's hello, everybody. It's really my distinct pleasure to deliver this lecture today. Here in the pretty picture, you see an offshore oil and gas platform getting its power from 3 offshore wind turbine generators in the North Sea, which is a great example of energy transition. The first thing I'd like to say today is thank you to my parents and my family certainly the Buchanan Lecture Selection Committee, BP America, and all my colleagues at BP and industry who made my career what it is. In particular, I'd like to recognize Don Murph and Alan Young. They are both recipients of the Distinguished Graduate Award from the Zachary Department of Civil Engineering. In the spring of 1990, Don was an adjunct professor at Texas A&M, and he taught a class on marine foundations, and he's the one that got me hooked. And I knew that if there was a job in the offshore industry, that's the job I wanted. And those two gentlemen have been tremendous mentors to me. I would be remiss, of course, if I didn't say thank you to Dr. Briot. This is the letter I received in France back in 1899 from Dr. Briot, welcoming me to Texas A&M University and assuring me of any further help that I may need in preparing for my studies at Texas A&M University. And this is the note I found on my desk in 1992 from Dr. Briot again. Dear Philippe, Amoco has an opening in the Research Geotech Division. If you wish to apply, send a letter with your bio data. Looks like a great job. It was a good job. It was a great job. I applied and I got the job, and Amoco merged with BP in 1999, and this is still the job I have today. So thank you, Dr. Briot, for welcoming me to Texas A&M and helping me find a job all those years ago. Now, let's talk about the world energy transition. I think it's a tremendously exciting time to be in the energy business. And I'd like to show you this graph here. This shows the share of the world energy of oil. Oil reached 1% market share in 1877. And you can see that it took more than 40 years for oil to reach 10% market share. This is the same graph for gas, which reached 1% market share in 1899. And you can see that 50 years later, gas still had not reached 10% market share. You can see the same graph for nuclear energy, never quite got to a 10% market share. And this is the graph for renewable energy, which reached 1% market share in 2006. What's fascinating is the predictions as to the growth of renewable energy. It is predicted to reach 10% market share in 2031, just 25 years after reaching 1% market share. So the conclusion is that renewables, which include wind, solar, geothermal, biomass, and biofuels, are set to penetrate the global energy system more quickly than any fuel in history. I found that fact absolutely fascinating. So the portion of renewable energy that's going to be of interest to us today is the offshore wind energy. So we will first look at the structures that we used to develop both oil and gas projects and offshore wind projects. So the simplest of structures are the monopod and multipod structures. In the oil, you can see examples from the oil and gas business here. This is a monopile. We call them freestanding caissons. This is a multipod structure. They represent only a few % of all the platforms, and we use them in water depth that are very shallow, say less than 50 meters. In the offshore wind energy sector, monopiles are extensively used. They represent about 82% of all the turbine foundation because they are very easy to fabricate, and the industry has become very efficient at procuring and installing them. Tripods are also used a little bit, but all the structures are used in very shallow water depth, less than 35 meters. When the water depth gets a little deeper, we use jacket structures. In the oil and gas sector, those are just steel tubular structures that you see here. They represent 95% of all platforms. They are used in water depth up to 411 meters, and most of the time they are founded on the seafloor with open-ended steel tubular piles. In the offshore wind sector, jackets are also used. They represent about 10% of all platforms, and so far they've been used in water depth up to 60 meters. Mostly, again, they are founded on driven piles. So these are the main types of structure. What's fascinating is that things can get very big in the offshore industry. You can see the world record jacket, the Bullwinkle jacket, 411 meters height, and it's being towed to the site here. You can see the cars on the parking lot to give the scale of truly how gigantic this structure is. Those big structures can be anchored with big piles. So here are typical dimensions. In the oil and gas business, we have diameters up to 2.5 meters, length of up to 140 meters. So the L over D ratio, the aspect ratio, is typically greater than 30. So those piles can be long and are called long and flexible. So you can see an example here on the barge. This is about 140 meters long pile, about 1.5 football field, and for scale, you can see the people here standing on the barge. The capacities are also very large, up to 100 meganewton. In the offshore wind industry, the diameters are much bigger because we need the monopiles to be stiff and to have the right natural period. And the best way to do that is to have a very large diameter. The vertical loads are not very high, so the embedment length is less, up to 40 meters. So the aspect ratio, the L over D, is between 2 and 6, and those piles are short and rigid. So we'll explore in a little while the difference between long and flexible piles and short and rigid piles. Now, one of the consequences of this large sizes is that we cannot perform full-size pile load tests. We cannot find the sites and the machines that can apply those loads onshore. So this is not an option for the offshore industry. Now, the first topic I'd like to talk about today is the design of axially loaded piles in silica sand. Most offshore piles have been designed with the American Petroleum Institute, the API method that we've used since 1969. Very simply, the method says that the unit friction along the pile is given by the coefficient of lateral pressure times the vertical effective stress times the tangent of the interface friction angle, and that has to be less than the limiting value. Similarly, the unit end bearing Q is given by a bearing capacity factor times the vertical effective stress at the tip of the pile, and that has to be less than the limiting value. And all those parameters that you need are given in the codes and standards as a function of sand relative density. Very simple equations. So a lot of authors over the years have investigated how well the method is doing. So to do that, you take a database, and you can see various databases here used by various investigators. And the graph shows here on the y-axis the ratio of measured capacity over calculated capacity with the API method. So if the ratio is less than 1, the capacity is overestimated. If it's greater than 1, the capacity is underestimated. And this ratio is given as a function of the sand relative density. This is for piles in tension, and this is for piles in compression. So what do you see when you look at those graphs? Well, you see that for dense and very dense sand, the capacity is underestimated, sometimes grossly. For this particular data point here, the capacity is underestimated by a factor of 5. What you also see is that for loose and medium dense sands, the capacity is potentially overestimated. But generally speaking, you look at this graph and you tell yourself, you know, it's not looking particularly impressive in terms of ability to predict capacity. So here are a few thoughts on the API method. Why have we been using it for so long? Well, it does provide a reliable, sometimes overly conservative though, capacity estimate for open-ended tubular steel piles loaded in compression in medium dense to very dense sand. And that's the typical offshore design case. So typically offshore, we are in this little box here for dense, very dense, and medium dense sands. However, the method does not capture the physics of how friction and end bearing develop. It's very difficult to justify why the friction and the end bearing are proportional to the effective stress, which varies linearly with depth almost. It's difficult also to defend the existence of limiting value both for the friction and the end bearing. Therefore, because we don't understand, because the method does not capture the physics, it is difficult to extrapolate the method outside the database of pile load tests to design very large diameter piles. The industry also decided in the 90s that it needed increased efficiencies. In other words, the conservatism in the method was too high, and we needed to have more efficient method. Which brings me to CPT design method. So CPT-based methods, there are many of those. You can see a partial list here. The ones that are highlighted have an offshore flavor, and the four that I will discuss today are highlighted in red: the Fugro method, the ICP, Imperial College Pile method, the UWA, University of Western Australia method, and the NGI, the Norwegian Geotechnical Institute method. Those four methods were developed in between 1995 and 2005, but the key point is that each method was developed from a different database. And in 2005, in the industry, there really was no consensus as to which method was the best. And there was a little bit of hiatus periods between 2005 and 2014 where basically the industry agreed to disagree on which method to use. Then there was a joint industry project, a JIP, initiated in 2014 to develop a unified, non-associated CPT-based design methods for piles and sand. Non-associated, we mean that the method does not have the name of a contractor or a particular university. It's just known as the unified CPT method. So the first step was to develop a unified database of pile load tests. And many people thought that could never be done, that the industry could never agree on a set of unified database. But that took 3 years. But at the end of 3 years, we ended up with 71 tests on open-ended and closed-ended piles, from which we could develop the unified method. So just to give you an example, these are the compression tests on open-ended steel tubular piles that have been used over time. You can see the tests that were used to develop the ICP method. You can see the tests that were used to develop the NGI method, the tests used to develop the Fugro method, and the tests used to develop the UWA method. So after 3 years of discussion, these are the tests that the industry finally agreed were going to be in the unified database, 13 tests. And this was a landmark achievement, and this unified database was published in 2017. So if you look at this unified database, what do you see in terms of pile dimensions? Well, here are the diameters and the length of all the piles in the database. So all but one have a diameter of less than 1 meter and a length of less than 40 meters. Now, those dimensions have nothing to do with typical dimensions for an offshore wind monopile, an oil and gas jacket pile, or an offshore wind jacket pile, except for one test. There's only one test, the Trans-Tokyo Bay test, that has reasonable dimensions. Now, when you look at the capacity in the database, whether in compression or in tension, you can see that most of the tests in the database have a measured capacity of less than 5 meganewtons. Whereas in practice, we typically have to design those piles for ultimate capacities between 30 and 100 meganewton. And again, there is only the Trans-Tokyo Bay that fits a reasonable real case. So those are the key challenges. After decades of testing piles and sands, we only have one test that resembles an offshore design condition. Therefore, the unified method needs to capture the physical processes that control friction and end bearing, and needs to understand how those processes extrapolate from the database to the pile design condition. So here are two of those fundamental processes that I'd like to present to you, illustrated by a test at the Labenne site in France. You can see the cone tip resistance, QC, at the site, and you can see the profiles of local shear stresses that were measured by the instrumented pile that you see here, during installation. So the first observation is the shape of those profiles is very similar to the shape of the tip resistance. Therefore, the friction at failure should be closely correlated to the cone tip resistance. That's the first principle. The second principle is if you look at a particular depth, say 2 meters here, you can see that those measurements are not constant. So what's happening is when you install the pile, this first instrumentation panel here in blue, when it reaches 2 meters, will measure that much friction. But when the red one comes to 2 meters, it only measures that much friction. And when the green sensor gets to 2 meters, it only measures that much friction. So the phenomenon that you see here is called friction fatigue. At a given depth, the shear stress at failure decreases as more pile is driven past that depth because of a continuing decrease in the normal stress against the pile at that depth. That's a very important phenomenon. So we typically capture it with this little h parameter, which is the height above the pile tip that is of interest to you. So to give you an example of the improvement with those CPT methods, let's look at some results from the Euripides pile load test, which were performed in the 90s. So you can see within the depth of interest, the tip resistance envelope, we are dealing with dense and very dense sands. And here is an example of test results. So this was a compression test. And here is the friction, the unit friction in compression that was measured at failure. And this is a profile that is predicted with the API method. So all those vertical lines are just here the limiting value of the API method. So you can see that the use of limiting value does not bear any resemblance to what we actually observe in the field. And you can start to understand why the API method can grossly underestimate the capacity of piles in dense to very dense sand. Now, if you look at the friction profile predicted by the 4 CPT method, here they are. They are all different, but they will all give you something that is closer to what was actually measured. So that's the improvement with CPT-based design methods. Now, let's look at what the unified method does to calculate the ultimate friction. This is the typical development of friction along the pile during testing. This is the local shear stress as a function of the radial effective stress. My job is to predict this point here, which is the failure point, the shear stress at failure, the maximum shear stress. How do I do that? Well, first I calculate the radial effective stress after installation and equilibrium, which is the start point of this curve here. And then I calculate the change in radial effective stress due to the dilation of the sand during loading. That gives me this point. And then I multiply all this by the tangent of the interface friction angle, and I get this point. So this is essentially what the unified method does. This is a Coulomb type of friction where the friction is equal to the normal stress, those two components, or the radial stress in this case, times the tangent of the interface friction angle. And there is a load factor in front of it because the friction in tension is less than the friction in compression. So here's a little bit more detail about the equation. This is the first component here. You can see that is directly proportional to the cone tip resistance. And you can see the friction fatigue term and this little h parameter that I was telling you about earlier. This is how friction fatigue is captured. This is the second component here that we need to calculate. Again, this is the cone tip resistance. And this is the pile diameter here. So you can see we now understand how those components vary with diameter. So we can extrapolate from small diameter in the database to large diameter in real life. The angle of interface friction, we debated for decades whether or not this interface friction angle was dependent on the sand grain size distribution and the D50 parameter. And after decades of discussion, we agreed that actually, no, it doesn't. That's because when you drive the pile, you have some grain crushing, and the grain size distribution after driving is not the same as the one you had before driving. So in the unified method, we just used a constant value of 29 degrees. This is the equation for the end bearing, and you can see that the end bearing is directly proportional to the cone tip resistance. So if you look at the unified method and you look at statistics using the unified database, you can see that with the unified method, we get a mean value of calculated versus measured of 1.05, which is very close to 1, the ideal value. But the big win is that we have a very low coefficient of variation, 0.24. This is a marked improvement upon the API method, which had a bias of 1.66 and a COV of 0.56. So to illustrate that visually, this is the same graph I showed you earlier, except now I'm plotting this using the unified database. So again, this is the measured over the calculated capacity using the API method as a function of sand relative density. So again, you can see the conservatism of the method. If I use the same tests using the unified CPT method, you can see that now I do a much better job of matching the measured capacity with the calculated capacity, regardless of the sand relative density. That's the big win. Now, the eagle eyes will notice that there is one data point that is still over predicted here, and that's the Padre Island test, which was tested only 2 days after being driven, whereas the method gives you the capacity 14 days after driving. So we're confident that if the pile had been tested 14 days after driving, we would have gotten a much higher capacity. So what are the benefits of CPT-based design methods? We have now an improved understanding of the physical mechanisms that govern friction and bearing. Therefore, we have confidence in extrapolating the method to the design of very large diameter piles. We have achieved now a consensus in the offshore industry, which allows us to codify this method in ISO and API standards as the main method. We've improved efficiencies in design. That is, for a given load, we have a shorter pile with the same reliability. We've improved efficiencies in assessment. That is, for an existing pile, we're able to justify a higher capacity with the same reliability. We've removed some of the unconservatism of the API method for piles in loose and medium dense sands. And finally, this method is equally applicable whether it's an oil and gas or an offshore structure. This is an example here of an oil and gas, of an offshore wind jacket. So what's fascinating is if you look at the timeline of the development and codification of offshore CPT method, between the time we did those key instrumented pile load tests in the 90s to the time we will publish a codified method in 2022, it is a 30-year journey. You see, it's easy, or it's one thing to say the API method does not work very well and needs to be replaced, but it's quite another to agree on what the replacement method should be. So it's a landmark achievement for us in the offshore industry, which is why I'm really excited to share it with you today. So let's switch topic now, and the second topic I'd like to address is the laterally loaded pile design in clay. So most of the piles offshore have been designed using what's called beam column analysis and PY curves. In beam column analysis, the pile, which is loaded laterally, is modeled as a beam, and the soil is modeled as a series of nonlinear springs that we call PY springs, and they describe the development of the lateral soil reaction, P, as a function of the lateral pile displacement, Y. So those methods are applicable and appropriate for the analysis of long, flexible piles. The soil is assumed to move only laterally. So to model it, I need to use only a lateral springs. The pile tip does not move, so I do not need to model it in my model. The PY curves that are in current API and ISO codes were based and developed from limited tests performed in the late 50s and early 60s, published by Professor Matlock in 1970 and included in API practice in 1972. They work well for us, but they've also been widely documented to underpredict both the soil stiffness and the soil strength. So why have we been using them for 50 years? Well, that's because they typically overpredict the maximum bending moment in the pile. So most of the time they will put us into a safe design condition, although the conservatism can be excessive. So it's really exciting to share with you that next year in the ISO codes, we will have a new set of PY curve for clays for 3 loading conditions: monotonic loading, cyclic loading, and fatigue loading. And those curves are based on some of the work that myself and others have done over the years. So the first job is to try to predict, again, failure, the ultimate lateral bearing capacity of the pile. And the second job is trying to predict the shape of that PY curve. So let's start with trying to predict the ultimate bearing capacity. For long and flexible piles, you basically have 2 types of failure mechanism. If there is no gapping, no gap opening on the backside of the pile, you have 2 wedges that form in the soil close to the ground surface. We call that the wedge failure. And later on, deeper, farther from the surface, the mechanism changes to a flow around soil mechanism around the pile. If you have a gap on the backside, you have only 1 wedge, but it's essentially the same thing. 1 wedge close to the surface and a little deeper, what's called a flow around mechanism. So how do we calculate the ultimate soil reaction? PU, very simple. It's the soil shear strength times the diameter times a bearing capacity factor. So the name of the game is to try to calculate this bearing capacity factor. So the new method we'll use in the wedge failure results from finite elements and upper bound limit analysis. And for the flow around mechanism, it will use results from upper bound limit analysis. The bottom line is the bearing capacity factor that you will calculate with the new method is higher than the bearing capacity factor that you get from existing curve and the method developed by Professor Matlock. So how do we get the shape of the PY curve? Well, we use what's called a direct simple shear test in the laboratory. So we perform this test on a clay sample in the lab, and we measure a normalized stress strain curve that you see here. We use this stress strain curve to define hardening properties in the plasticity soil models. We run finite elements analysis where we push the pile laterally and we measure the resistance of the soil. And from this, we obtain numerically a normalized PY curves, development of P as a function of the lateral displacement. And what we've developed is a method, a scaling method, for which each point on the normalized DSS curve is transformed into an equivalent point into the normalized PY curve. So that's how you get the shape of the PY curve. Now, in the new ISO code, you will have 6 default PY curves that will be given as a function of soil plasticity and over consolidation ratio, and those will replace the curves of Professor Matlock. So what do those curves look like? These are an example of curves for the flow around mechanism. This is the typical curve that you will get with the current method. This is the typical curve you will get with the new method. So it is stronger, the NP factor is higher, and it is stiffer for very small lateral displacement. This is all for monotonic load. But this is not the end of the story, because when we design offshore structures, we have to design them against hurricane, typhoon, cyclones, and you can see the track of those here over the last 50 years. And even in areas where you have none of those, for example, the North Sea, you have winter storms. So this is a little video of a winter storm hitting a platform in the North Sea, and you can see a large wave that's coming here, which is about 20 meters in height. So this is a 20-meter high wave hitting a platform and getting just barely under the deck, the lower deck of the platform. So there is no question that the loads that the platforms are experiencing are cyclic in nature. So what do we do to understand those? Well, it brings us to understanding the behavior of clay under cyclic loads. And again, we use the DSS test to do that. So cyclic effects are interesting. They are the combination of two effects. There's the rate effects, which say that the shear strength increases if the rate of shearing increases. That's because soil are viscous materials. And there is the cyclic degradation effect that says that the shear strength decreases if the number of cycles increases. That's because the soil gets remolded and loses its structure with every cycle. So the net effect is not always obvious. So how do we investigate that? Well, we take a sample and we do a cyclic DSS test. So we apply a cyclic shear stress, a mean stress, and a cyclic stress. And we measure the response of the soil, which is the strain. So you can see here the development of the mean strain and the cyclic strain with time. So now we have shear stress and shear strain. So we can plot one against the other and we get stress strain curves, cyclic. This is the first cycle, and this is how it progresses with cycle. We continue the test until we reach a shear strain value of 15%, and we arbitrarily call that failure. And then we measure the cyclic shear strength. And from those type of tests, we've done hundreds of those, thousands of those over the last decades. You can construct what's called interaction diagram. So they're a little tricky to understand if you're not familiar with them, but let's give it a try here. What you have here on the horizontal axis is the mean stress that you apply in your test divided by the static strength. And on the y-axis, you have the ratio of the cyclic strength over the monotonic strength. And here you have curves that give you the number of cycles that you can resist for Drammen clay and Gulf of Mexico clay. So for example, if you were running a DSS test with a mean stress about 25% of the shear strength, and you wanted to resist 1,000 cycles, this graph tells you that your cyclic strength is only about 75% of the monotonic strength. So it's less. So cyclic degradation governs. However, if you have a mean stress of 50% of the shear strength, and you only need to resist 10 cycles, if you have a Gulf of Mexico clay, this graph tells you that the cyclic strength is 1.2 or 20% higher than the monotonic strength. That's because rate effect govern. So there's a whole area of the diagram here for which the cyclic strength is higher than the monotonic strength. So why is that? Well, when you measure the shear strength in a monotonic DSS test, you shear the sample at a rate of about 5% per hour, and the sample reaches failure in about 1 to 3 hours. However, when you do the cyclic test, you shear the sample with a load period of 10 seconds. And if you only need to resist 10 cycles, well, the sample reaches failure in 2 minutes. So you have tremendous rate effect, viscous effect, and that's the difference between a time to failure of 2 minutes versus 3 hours. So where are we for a typical loading that is experienced by a jacket offshore under hurricanes or North Sea winter storm? Well, actually, we're in this part of the diagram. So we don't have that many cycles at the maximum load level. So this is a very important observation. For typical offshore jacket, the cyclic loading conditions are such that the cyclic strength is higher than the monotonic strength. Now, this is where we are for a full-size jacket. And this is where Professor Matlock was when he ran his tests in the late 50s, early 60s. He performed cyclic tests, but he had hundreds of cycles. So we know now, we didn't at the time, but we know now that those hundreds of cycles really are not representative of what is experienced by a platform offshore. But you can see that for hundreds of cycles, this diagram will tell you that the cyclic strength is less than the monotonic strength. So what's the impact on the PY curve? This is the curve, this is the monotonic curve I just showed you with the current methodology for monotonic load. And this is the same curve for cyclic load. So you can see the cyclic curve is less than the monotonic. And that's because Professor Matlock run tests with hundreds of cycles, and the shear strength is less in cycling than it is for monotonic load. This is the new monotonic curve that I showed you earlier. Again, it is stronger and stiffer, but the key difference is now, because we're here for offshore platform, the cyclic curve is actually stiffer and stronger than the monotonic one, because the shear strength for real loading is higher during cyclic loading than it is in monotonic loading because of rate effects. So the way this will work in ISO is that you get this monotonic curve here, and we derived P and Y modifier multiplication factor, if you want, that gets you from this point to this point. But again, the key difference is in the current and old model, the cyclic curves are softer than the monotonic curves. In the new model, the cyclic curve will be stiffer than the monotonic curve. Now, to try to look at the fatigue curves, they were developed from centrifuge tests and direct measurements with a novel laboratory testing apparatus. So it's not every day that we develop a new lab apparatus, and I'm excited to share this one with you. So this is the source sample here. You can see the dimensions. You can consolidate the sample to a given effective stress. You insert a rod into the sample, and you cycle that rod within the sample, and you measure the resistance on the rod, which gives you the P, and you measure the displacement of the rod, which gives you the Y. So you can see the source sample here mounted in the apparatus. This is what it looks like in the lab. So this is a little video of a fatigue PY curve test being performed. You can see the rod here moving back and forth in the sample. So we do that for a couple of thousand cycles. Again here, hopefully that's coming through okay. And then we get equilibrium, and then we get the fatigue curves. So this apparatus here was developed through a collaboration between BP and the Norwegian Geotechnical Institute. It is available for commercial purposes. So if you are interested in measuring your site-specific fatigue PY curve, then you can contact the NGI lab in Oslo, and they'll be happy to help you. Now, I told you earlier that because the piles are so big, we cannot do full-size pile load testing on them. We can't, but Mother Nature can, and it does that through hurricanes, particularly in the Gulf of Mexico. So you can see the names and tracks of some of the most famous and significant hurricanes of the last few decades. If you go offshore after one of those hurricanes and you look at a destroyed platform, this is typically what you will see. You will see that all the damage, this is the destroyed platform here, and this is a platform that's still standing right beside it, but all the damage in this platform is in the jacket itself, in the steel tubular structure. There is little to no damage in the pile foundation at the seafloor. However, if you do a numerical model using the current PY curve, you will predict the exact opposite. You will predict little to no damage in the steel tubular structure, and you will predict all the damage to be in the piles. So the conclusion is that with the current PY curve models, we are not able to replicate the failure mechanisms and the damage that we observe in the field, which is not very satisfactory. So to try to validate those new PY curves that I just described to you, we had a study with KBR a couple of years ago looking at hindcasting the performance of various structures in the Gulf of Mexico after hurricanes. So you can see here a monopile, a freestanding caisson, that was damaged by Hurricane Andrew in 1992. It was found leaning 15 degrees at the waterline. So this is not the actual caisson, but this is a caisson similar to it. This is what you would find when you go offshore after the hurricane. So what we did are what we call dynamic pushover analysis using two sets of PY spring, the current monotonic PY curve, and using the future cyclic curve. So you can see here the waves hitting the platform. So using the current monotonic PY curve, you can see that the pile is starting to plastically hinge. You can see that the pile above it is starting to yield, but close to the seafloor, you see no yielding in the pile because the soil's resistance is too small. The PY spring is too soft. With the new curves, you can see that the plastic hinge is also forming a little higher, but now you see that the pile is yielding all the way to the seafloor because the PY springs are stronger. And obviously, you can see that the caisson is starting to lean more and more with the old curves than it is with the new curves. So at the end of the analysis, using the current curves, we would predict that caisson to be leaning 34 degrees after the hurricane. With the new curves, the cyclic curves will predict it will be leaning 16 degrees. And I've told you already that the field observation was 15 degrees. So this is really exciting. For the first time, we are able to hindcast or reproduce the observed damage that we see after hurricanes. Another example is this jacket, which was damaged by Hurricane Gustav and Ike, but mainly Hurricane Ike in 2008. So what kind of damage was observed on this platform? Close to the waterline, you had joint failures and separated members. You had cracks at some of the connections. Some of the braces or members were buckled. So you can see that this member here is no longer horizontal. It is bowed because it has buckled in compression. What is so closer to the seafloor, we see cracked and damaged joints right there. And very importantly, we see no indication of pile foundation failure or lateral displacement at the seafloor. We didn't see that in any of the underwater inspection. So we can do the same thing. We can do dynamic pushover analysis using the current iso springs and the future iso springs. What do we see? With the current spring, we predict a lot of hinging and damage in the piles below the seafloor and some damage in the steel tubular structure. With the new springs, we predict much less damage in the piles and much more damage in the structure. If you look at the pile displacement at the seafloor with time, so with the new spring, you see each wave here passing through, but you see displacement, horizontal displacement of about 0.1 meter with the new spring versus displacement of 0.4, 0.5 meter with the current springs. So what we would say is that the hindcast with the future cyclic PY curve is more consistent with the fact that no noticeable pile lateral displacement was reported. So how well did we do predicting the damage with the new springs? Well, we have little damage in the pile, just a little bit of yielding, and that's consistent with the observation. And this buckled member here that was predicted only with the future cyclic PY springs, well, that's this member here. It actually did buckle. So again, we are able to much more accurately reproduce the damage and the behavior that we see with those new PY spring. So that reminds me of one of my favorite quotes from Oscar Wilde: "Experience is the hardest kind of teacher. It gives you the test first and the lesson afterward." So those hurricanes gave us the test, which was to reproduce the damage they had caused, and we failed the test. We could not do that. But we learned the lesson, which is we improved our PY curves, and now we can. So this is, again, very exciting. Now, to try to validate the fatigue curve, now we're not talking about damage under hurricane, we're talking about vibration data and recording of natural period of this particular structure here, which is a tripod in the Gulf of Mexico. So again, you can do numerical analysis with two sets of springs. So this is an analysis in the torsional mode. The displacement that you'll see are exaggerated, but you see the platform vibrating in the torsional mode, and you can see the pile displacement here below the seafloor. With the new springs, you see much less displacement and a much stiffer structure because the springs are stronger. So how did we do? This is the field measurements. So these are the three measured period, 1.071 and 0.76 seconds. And these are the calculated periods with the new springs. So you can see that at least for 2 out of the 3 vibration modes, we're able to match the measurement within 1%. Whereas with the existing curves, we are about 10% off. So the difference between 10% and 1% may not seem like much to you, but it is of huge importance in the offshore wind industry and for fatigue analysis, where it is absolutely crucial to be able to calculate the correct natural period of the structure. So this is just an overview to make you comfortable with those new PY curves. Now I'd like to talk a little bit about the project PISA, which was performed within the offshore wind community, and they developed a new approach for offshore wind monopile design applications. They did tests in sands and in clays, but we're only talking about the testing at the Cowden site in Glacial Till here. You can see the shear strength profile and the small strain stiffness profile, the interpreted value, and you can see all the scatter that is at the site, which tells you about the difficulties in characterizing Glacial Till. So you can see they did a series of tests with pile diameters with up to 2 meters and aspect ratios between 3 and 10, which are appropriate for offshore wind monopile design. So what is the PISA design method? The only one that's been published to date is the one for monotonic loads. So basically, with the PISA method, you run a series of 3-dimensional finite element analysis for your given site condition and for a range of diameter, length, load application heights, and wall thickness that you think are going to cover all the possibilities of your problem. If you do that, you will see that the soil again along the pile wall not only moves horizontally but also vertically. That's because the caisson is short and rigid. And you will also see that the base now moves horizontally and also rotates. So to capture all those soil displacements, from each of the finite element analysis, you extract 4 types of soil reaction curve. One distributed lateral load reaction curve, one vertical reaction curve, and 2 reaction curve, the horizontal force and the moment at the pile base to capture the behavior of the pile tip. So you get all those curves and you curve fit them with an equation that is a conic equation that looks like this, that has 4 parameters. So all those soil reaction curves will look something like this. And you try to find empirical relationships for your site with all the piles that would apply to all the pile diameters, all the pile length. And at the end of the day, you generate a beam column model that has 4 reaction curves. So the idea is that in a practical design, instead of having to do thousands of 3D finite element model, now you can do thousands of beam column analysis, which are much more computationally efficient. But now you not only have 1 soil reaction curve, PY curves, you have 4 reaction curves. However, this distributed lateral load reaction curve is serving the exact same purpose as the PY curve that we used in the oil and gas industry. It models the lateral soil behavior. And again, if you look at the ultimate value of the soil resistance, you have to calculate this bearing capacity factor. So these are the equations that will be in ISO to calculate NP, never mind the details. And this is the empirical relationship that was published by the PISA project for the Cowden site. So you look at those 2 sets of equations, you say, oh my God, they look completely different. They're supposed to represent the same thing, the lateral pile soil reaction. How do they compare? Well, if you take the tests at the Cowden site, those 2 tests here, and you use the ISO method, you can calculate a lateral bearing capacity, NP, as a function of the normalized depth Z. You have this for those two piles. And this is the empirical relation I just showed you that was published for Cowden that applies to all pile diameters and length. So you can actually see, although they look completely different, they give you very similar results. The PISA project also did finite element analysis for what they call calibration piles. So these are bearing capacity factors that have been extracted from finite element analysis. Now you can see that at some depth, those values are very small, but these are the values that are around the rotation point of the short and rigid monopiles. So the lateral bearing has not been fully developed. So those data points here are neglected. So again, you can use the ISO method for the FEA soil condition, and you calculate those two profiles for those two calibration piles. So again, you get very good agreement in terms of calculating the ultimate bearing capacity between the PISA framework and the new ISO framework. In terms of the shape of the PY curves, in the ISO document, these are the three default shape of the curve that will be presented as for a plasticity indices greater than 30%. So this is the curve for OCR less than 2, OCR of 4, and OCR of 10. And these are the three curves for plasticity indices less than 30%, which are applicable to the Cowden site, which has a plasticity index of about 20%. And this is the formulation for PISA. This is the conic equation I mentioned earlier. That curve fits all the soil reactions. So P is, you have to solve this equation for P. This is a quadratic equation in hiding, so it's not too hard to do. But these are all the empirical rules for all those parameters here, Kp, that you have to plug in this equation. So again, you look at those two frameworks and you say, my gosh, they're supposed to represent the same thing, and they look completely different. So again, how do they compare? Well, for one of the Cowden tests that we looked at for one particular depth, this is the default ISO curve that you would use for an OCR of 2 and an OCR of 4. And this is the curve that was actually presented by the PISA project at a depth where the OCR is 3.7. So we have actually an excellent match between the two frameworks. A little higher in the pile, this is the default ISO curve for an OCR of 10 that would be recommended. And this is the curve that has been presented by PISA. So we're a little off on the ultimate capacity, but remember there's a lot of scatter in the shear strength. And we're a little off in the stiffness, but remember there's a lot of scatter in the small strain stiffness, which could move those points this way here. So overall, we're quite happy with how those two frameworks compare. If you try to compare the PISA finite element analysis results, these are all the PY curves normalized that were extracted from the FE analysis of PISA. And this is the default curve that will be recommended by ISO. So an excellent agreement. There is one curve here, the first curve that has an OCR of 3.5, this curve right there, and that curve should be closer to this curve here for ISO for OCR of 4. But the other ones are really very close to the ISO recommendation. So we have a paper that's been accepted for publication at OTC next year, where we will present all those details. They have not been published yet, so you heard it first here today. So what are the contributions of this lecture? I've told you about the unified CPT design methods for piles and sand, which was developed by the oil and gas industry, and which is equally applicable to offshore wind jacket piles and monopile design. If you have time to read only one reference, this is the one I would recommend you read. I've told you about the new ISO PY curves for long flexible piles and clays, again developed by the oil and gas industry, but also applicable for offshore wind jacket piles, but not for monopiles which have an L over D of less than 10. For those type of design conditions, you need to use more soil reaction curves. So you need to go from one reaction curve, the PY curve, to 4 reaction curve, for example, as per the PISA method. Other designers use only 3 curves, so there's not industry agreements on how many curves are really needed. Again, read the paper if you can wait until May of next year. This is an offshore technology conference paper that will have all those details. I've also told you about the PISA design method for clays, developed completely independently by the offshore wind industry. It's very satisfactory to see that the distributed lateral load reaction curves for the Cowden site are entirely consistent with the recommendation of the new ISO PY curves. We could use the PISA design method in the oil and gas industry if we have a foundation that has a similar geometry and aspect ratio. And again, this is one reference, a geotechnique paper that I would encourage you to read if you're interested. These are all the references I've quoted in the paper, in the lecture. Don't bother writing them down now. You can listen, you can view the recording of the lecture and write them down at your leisure later on. So if any of what I said is of interest to you, then I would recommend you check out this website, isfog2020.org. ISFOG stands for International Symposium on Frontiers in Offshore Geotechniques. The conference was supposed to take place face-to-face in August of 2020 in Austin. Obviously, that did not happen because of COVID, but we did publish the proceedings that you can purchase and where you will see 200 plus technical papers, 6 keynotes, and the 5th ISSMG Buchanan Lecture. We really hope to be able to have an in-person conference in Austin next year in late August. And to try to advertise the conference, we will be offering 6 webinars in 2022, free of charge, streamed live and updated to YouTube. So you can see we'll be offering 1 a month on a variety of topics. You can see the organizers and the presenters here. We'll talk about data science, cyclic loading, the new PY curves for piles and clays, the new CPT-based design method for piles and sands, and then we'll talk about 2 joint industry projects from the offshore wind industry, the Red Wind GIP and the PISA GIP. So all of this is organized by ASCE and the Geo Institute. So again, check this website. You can get the information to all this, the webinar and the how to register for the conference. I would like to leave you with a final thought that comes from Professor Jim Mitchell, who said that the greatest advances in geotechniques have come from 2 sources: the need to undertake projects in uncharted environments, such as the Arctic, the oceans, that's us, the offshore industry, and space, where there is little to no experience, but the risks are high. So I've illustrated those advances with pile designs in sand and PY curves in clay today, and post-failure investigations from which the reasons for the surprise are deduced. And again, I've illustrated this with the surprise, which was the fact that we could not hindcast the behavior that we observed after hurricane damages, but the reason is now been deduced, and we have upgraded and updated our PY curves model. So with this, I thank you one more time for having me as your Buchanan lecturer today. Thank you.
Thank you very much, Philippe. Wonderful lecture showing the evolution of offshore geotechnical projects and design, telling us about this success story, a 30-year success story, and also the trend towards renewable energy with the wind turbines. It's a true pleasure to know you as a brilliant engineer, as a close colleague and a friend. You should be extremely proud to find your name along those who gave the Buchanan Lecture before you, including Ralph Peck. I have a nice engraved plaque to give you to commemorate this honorific event. Here it is, and I will send it to you in the mail. The Buchanan Lecture is also awarded an honorarium, and I know that you've decided to give your honorarium as a contribution to the funds of the Buchanan Chair. We very much appreciate that. And you know, these funds support student research activities, including yours some time ago. Thank you again for preparing and delivering an excellent lecture.
My pleasure. Thank you.
Now, it's my pleasure to introduce Professor Ed Cording. Dr. Edward J. Cording is Professor Emeritus in the Department of Civil and Environmental Engineering at the University of Illinois at Urbana-Champaign, where he taught and conducted research in geotechnical engineering, concentrating in the areas of rock engineering and soil structure interaction. It is common for university professors to have a laboratory in a university building, but his laboratory has been in the field, where the action is, as Terzaghi put it, observing and analyzing the behavior of excavation, slopes, underground structures on projects ranging from large caverns in stress fracturing tuff in Nevada, deep rock tunnels in squeezing shales in the Uintah Mountains, shallow subway stations, caverns in metamorphic rock along the East Coast, shield tunnels in alluvial soils in Washington, D.C., and in the soft Chicago clay. His investigations on urban transit projects led to the development of criteria used in practice for assessing excavation and tunnel-induced ground movement and their effects on building distortion and damage. He is a member of the National Academy of Engineering and received the Moles Award for Outstanding Achievement in Construction in 2003, the Beavers Engineer Award in 2013, and the Outstanding Educator Award of the Underground Construction Association of SME in 2012. From ASCE, he received the Middlebrooks Award, the CAP Award, the Schnabel Award. He was selected to present the 2018 Muir Wood Lecture and the 2020 Terzaghi Lecture. His practice as a geotechnical consultant includes projects with pressurized tunnel boring machines in Cleveland, Columbus, New York City, Sacramento, San Jose, San Francisco, Vancouver, Washington, Seattle, Toronto, and Los Angeles. Obviously, he's an expert on tunneling, and it is my pleasure to now give the floor to Professor Cording to deliver his 2020 Terzaghi Lecture entitled Observing and Controlling Ground Behavior with Tunnel Boring Machines. Ed, the floor is yours.
Well, thank you very much, Jean-Louis. I appreciate the introduction. I also appreciate being able to listen in on the lecture. Philippe, I congratulate you for the honor that you've received here from Texas A&M. Very, very appropriate. I'm going to work on sharing the screen here for a moment, see if I can
go ahead.
Get this up. And there we go. And
very good.
And I do need to, yes.
Yeah, go full screen.
Yeah, full screen, just 1 second. Yeah, we're just about ready here. Okay. Okay, just a second here, just a moment. Here we go. Okay. Are you seeing the full screen now?
Yeah, we're seeing full screen.
Yeah, and so I think I'm ready to go ahead.
You go right ahead.
Thank you very much. Observing and controlling ground behavior with tunnel boring machines. And this was a lecture I gave it at the Terzaghi lecture a year and a half ago, just before everything shut down. And appreciate the invitation here to give it to you all at Texas A&M. It's a real privilege, and I do appreciate it. Okay, just a minute here. All right. Let me set up the screen just a second here, a little bit better for myself here, and I can, it'll hopefully work for you all. We're really witnesses to a revolution. People involved in tunneling and underground construction, geotechnical engineers and engineers, we are witnesses to a revolution in the ability to tunnel deep beneath waterways without the limitations of compressed air, multiple shifts, and the problems with compressed air. And we're able to tunnel at shallow depths in urban areas without damaging settlement. And it began almost 50 years ago with the pressurization of the face of the tunnel boring machine. And it has continued with the pressurization around the entire shield. There we go. Where we have what is essentially a fully pressurized envelope, and we are pressurizing not just the face, but the perimeter of the shield and the gap that is being grouted in the tail, grouting that under pressure. Fully pressurized envelope. And that is what is helping us essentially eliminate ground loss and reduce settlements that could damage structures. I'm going to talk a little bit about the largest tunnel boring machine that was ever advanced under an urban area, the 17.5 meter Alaskan Way project in Seattle. Was completed in 2017. And I wanted to just step back and take one brief look at where we started. In London, 11.6 meter, about 40 foot wide tunnel was built under the Thames River in 1843. It was largely completed, and it was built by Mark Isambard Brunel, who designed and constructed it, acted as the engineer and the contractor for the project. And he basically had a patent application that for a tunnel shield, and the application was to open the ground in such a manner that no more earth shall be displaced than is to be filled by the shell or the body of the tunnel. And he was not able to achieve that objective. There were 7 eruptions or inflows from the river, the Thames River, into the tunnel during construction. And he continued and completed that in 1843. At that time, I think he received the, he basically received from Queen Victoria, he received an honorarium, essentially what became, was essentially knighted by Queen Victoria in 1843. And I would think that they weren't quite done, but I would think that would, in our terminology, would at least be considered substantial completion. But we have still struggled over the last 200 years to meet that objective. And I want to talk about how we are doing that and how we are observing and controlling that ground behavior during tunneling, starting with pioneering observations that were done on the Chicago subway by Carl Terzaghi and Ralph Peck. And then the observations with open face shields. And we'll talk a bit about Washington Metro and Chicago clay tunnels. And then finally going to the observation and control that is achieved with the pressurized tunnel boring machines. Starting with Carl Terzaghi and Ralph Peck's work on the Chicago subway, it had not been done. Correlations between what was happening in the tunnel and at the surface really hadn't been handled much or evaluated at that time. And Terzaghi wanted to relate the tunnel construction to surface settlement. And so they conducted squeeze tests to measure the displacement into the clay, of the clay into the tunnel. And that allowed them to determine the volume of ground loss. They correlated this with construction methods and then observed that the support of the arch, the excavation procedure was not working. They reduced the settlement by correcting that, and they reduced the settlement from 4 to 2 inches. And then later, something that wasn't in the articles, publications that Terzaghi had produced back then, 1942, Peck looked at, was asked to evaluate why the settlements had increased from 2 to 5 inches again as they went deeper. And he went into the tunnel and he observed, it did essentially the squeeze test, but he focused his time on what was happening during construction. And the delay in filling this 5-inch gap between the liner plate and the soil was causing inward displacement. And the only support essentially was the air pressure, not the lining. The lining itself was free and not tied to the clay at that point. And so he reported on this and evaluated the displacements, and the correction of this reduced the settlements again from 5 inches back down to 2 inches. It was really, to me, interesting to see the way they approached the project. They were focused on looking at the construction, correlating that with the ground loss around the tunnel, looking at soil properties, particularly unconfined compressive strength and water content of the Chicago clay. And then they correlated all of that with the settlement at the surface and produced it on a single blueprint. To me, that was the essence of what we are trying to do today. They were in 1941, they were concerned with filling the gaps, and they were correlating on the results in a way that you could evaluate what was not just the measurement of the movements, but what was the cause. And today we basically have almost the same 2 points to make. We need to fill and pressurize the gaps to reduce settlements and essentially eliminate ground loss into those gaps. And we need to be correlating the ground movements with key tunnel boring machine parameters. And so we're working now with electronic data and several thousand tags on the tunnel boring machine, which are reading continuously various functions. So we have to sort that out and summarize it. And that's a real problem in our industry in underground construction of putting this together with the ground movements with what's happening out the tunnel boring machine. It's a real important part of assessing and correcting and controlling a tunnel boring machine. And so the second item that I wanted to cover then was the observations with open face shields. And what we found over the years that with trying to control ground loss was a continuing challenge. We had a situation where the face of the tunnel was not fully supported, and there are various methods used, but you have the risk of large local ground losses into the front of the tunnel boring machine. And you also had a problem with the regular ground loss. It's very hard to get ground losses down below about 2 inches because of the loss into the gaps around the machine. So we'll look at two cases. It was really a struggle and a continuing challenge. And I saw that from the 1970s into the 2000s, the difficulties we had with the open face tunnel boring machines. So we go to 1972 on the Washington Metro, and we had an objective of looking at the 3D movements around the tunnel, borehole extensometers and inclinometers. I think the first time that was all put together in a way where you could look at the total three-dimensional pattern of the ground movements of the tunnel boring machine advanced through the ground. And in this case, it was right in the middle of Lafayette Square in front of the White House, and we made those measurements sitting out there in Lafayette Square and watching protesters and supporters of the White House and its occupants jousting and moving around on the adjacent Pennsylvania Avenue. What we have here was the surface settlement was extremely large and it was 150 millimeters. And the question was really, what is causing this? And then the obvious solution, the obvious conclusion would be that you're getting a large ground losses into the front of that digger shield, that open face shield. And so we had an inclinometer right in front of the tunnel, and we drove right into that inclinometer and removed the torpedo before the casing was hit by the tunnel boring machine. And we were able to measure that displacement. It was only 6 millimeters. It confirmed that the face loss was not in the front of the machine, that we were getting ground loss. Something was happening around the tunnel boring machine. The deep anchor above the tunnel, measured with the extensometer, showed really large settlement of 330 millimeters. And what was happening was that tunnel boring machine was really a shield, not a real, what we'd call a real boring machine. It was an open face shield, was plowing through the ground because of the balance of the shield itself, and it was causing a settlement almost every time it went forward 4 feet. It would have a settlement there that was a couple of inches, and that was occurring as it went by. The pitch was much higher than the grade. Well, they corrected that on the second drive, and they reduced the settlements down to about 50 millimeters or 2 inches with that effort. And then I go on to another case where we're in the soft Chicago clay with a smaller diameter, love it, with a cutter head or wheel at the front. And this was not a pressurized machine. So when the muck goes into the front of the machine, it's not, you have those doors that open and they aren't completely supporting the ground. And so you have a situation where there can be ground loss out in front of the tunnel boring machine. But as you look at the data, you can see that the deep anchor is moving down pretty much at the time that we were passing by with the shield body itself. And so you can see there that settlement was on the order of there we go, the settlement of about 38 millimeters. And it was due to that gap that's between the behind the tunnel cutter head and the shield body, and you have to over excavate a little bit in order to reduce friction and make the turns. And so you have that 19 millimeter gap, and that is really what's happening, causing settlement there that's in excess of 1 inch just due to that gap. And then installing the lining was causing some additional ground loss. But what we have is a situation when we look at everything that was going on with those tunnel boring machines and shields, at that time was that we always lost that gap. It could not fill the gap because everything was open and anything you tried to do in there would flow out and away. And so that was really the kind of the major issue, in addition to conditions occurring in the front of the shield, which would cause the large ground loss into the open face of the tunnel boring machine or shield. And so we had piezometers in the clay, which were really basically monitoring undrained behavior. They're looking at the stress changes as the tunnel boring machine passes, essentially. And due to changes in the mean stress and in some cases, to some extent, the shear stress. But you have an increase as you push forward, and then the pressures would drop over the shield because it's unloaded, and then pressures would increase again. And when you got through the project or through that advance of the tunnel boring machine by that location, if the pore water pressures were greater than that, than the reference pressure, then you would have a situation where the pressures are going to have to, the pore pressures will drop, of course, and drain, and you will get more consolidation. In this case, we had a situation where an additional inch of settlement occurred due to the consolidation. So the piezometers in the soft clay are measuring those undrained stress changes. We're going to also look at the case where the piezometers in sand are measuring the flow of the materials from the face and shield and causing dynamic increases in pore water pressures around the tunnel boring machine. And you have to essentially maintain those pressures on the tunnel boring machine with an outward gradient sufficient to support the soil outside and to balance the water pressure. So the lesson really from looking at the history is that the liner plate tunnels in Chicago and the later work is that you really have to support the face and fill the gaps. The two places. The face support in the Chicago tunnels was compressed air. The lining gap was minimized. They filled with pea gravel immediately to limit the movements. And that was really a source of a lot of the settlement that did occur at the ground surface. The open face shields that we were talking about in the last 50 years, we really had the potential in the face for the large ground loss and flow into the face. And then that overcut gap was not filled, and it was inevitably the cause of ground loss and settlements at the surface that exceeded at least the levels that would be required to prevent damage. And so we look at the pressure face at fully pressurized tunnel boring machines. They go from pressurizing the face to prevent that inflow, and then we now are pressurizing the gaps to prevent the loss into the gaps and reduce the settlements. And so that's the revolution that has been happening here, where we are now tunneling under major structures, urban areas with large diameter machines and small cover without damaging settlement. So let's just look at the profile here, just to look at what is happening with the pressure face tunnel boring machine, the sort of thing that has been in use now for over 40 years. The chamber in the front is filled with this pressurized muck. Essentially, the excavated material is conditioned with a foam. It's a water, essentially a water soap mix surfactant that interacts with the soil to provide something that is perhaps a viscous fluid. The polymers and bentonite that may be used to make it and condition it and make it into a viscous fluid that, when it's pressurized, it does support the face. The screw removes the muck and provides a back pressure. And so you have then a pressure applied at the face to balance the groundwater pressures and the active earth pressures. And so you really need to monitor that pressure, and the key means of monitoring it and controlling the tunnel boring machine are the face pressure gauges. And you'll have on a 20-foot machine, 2 at the top, 2 in the middle, and 2 at the bottom. And you have to maintain those pressures above the groundwater pressures and any active pressure of material that could just flow in under as an active force. The other thing that you do is you check on the back end of the machine on the weight scales to determine the volume of material, or the weight, calculate the volume of material, compare that to the volume of your advance to make sure that you're not excavating more material than should be excavated within the shield. Essentially, you're trying to meet Brunel's criteria to not take out anything more than that, than the ground, and any more ground than around the perimeter of that shield. So as we go on from just looking at the pressure face, we need to start thinking and be concerned with what's happening with around the shield body. And so we have basically that segmental lining that's erected in the tail of the shield. And then grout is injected under pressure through the back end of that tail, or that black zone there, the back end of the shield itself, to fill the gap as the TBM advances. It's coordinated with the TBM advance. The TBM does not move forward unless that gap is filled. And that gap is on the order of 4 or 5 inches and would cause extremely large settlement if it's not filled. The other is the gap around the shield perimeter itself, right behind the cutter head, and that the muck can flow into that gap and actually can fill it, but it isn't always consistent. And particularly when you have coarse materials, they're not going to be able to flow around the perimeter from the cutter head into that gap. And so what we have been requiring on our projects, and what was required and used throughout the large diameter tunnel in Seattle construction, was to pump a slurry of bentonite into the gap continuously as you advance the tunnel boring machine, and to maintain that pressure so that you would essentially support the ground above the shield with that pressure. And the monitoring then was, again, looking at those face pressure gauges, the borehole extensometers. We've added piezometers to that to monitor what's happening around the shield in terms of the pore pressures, which has been a very useful piece of information for us on our projects. It's something that's not been done really only relatively recently on our projects. And then the other is that we put pressure gauges on the body of the shield. And that allows us to monitor what sort of pressures we have that are supporting the ground above. We're also using horizontal inclinometers used to put in the horizontally directionally drilled holes, HDD, put them out several hundreds of feet to provide a continuous record. It's been an extremely valuable piece of information, particularly when you put something out like that out of the shafts. So all of that is what we're doing with the pressure face TBMs. And what we're seeing is increasing control, decreasing ground loss, and increasing diameters are being used in the last 20 years. And I wanted to talk about the bottom 3 cases. The upper Porto, Barcelona in particular, were cases where things were being tried out, and they were really pioneers in controlling the ground. And Barcelona was one of the largest machines at that time, 10, 12 years ago, they were basically working with 12-meter tunnel boring machines, 40-foot diameter tunnel boring machines. And we'll look at first at an example about 10 years ago in Toronto at York University. And then I want to talk about Alaskan Way in a little more detail, and then finally some things that are happening presently, particularly on the LA Metro project, where I've been following the construction of on all of the segments that are under construction at the present time. In Toronto, they basically are driving with two earth pressure ballast tunnel boring machines that are 6 meters in diameter. They had to pass underneath the spread foundations of the Schulich building at York University. They were only 6 meters below. And there was a plan to put in compensation grouting with hundreds of horizontal pipes beneath the foundations of the TBM pass. They basically the effort there was to hold the settlements and the heave after the TBM had gone through with the up and down with the compensation grouting, to end up with less than 10 millimeters of settlement above this very major building on the university campus. The tunnel boring machines were advancing toward that area. They'd had some problems with the compensation grout subcontractor, had some issues where it did not perform. And the compensation grout pipes were not in place as the TBMs approached and were within about 150 meters of the building. The contractor was doing pretty well. Ground movements were relatively small. He was at greater depth, of course, than the 6 meters to the foundations. And he requested that he advance beneath the building without compensation grouting. And so Toronto Transit basically proposed they have a test section to check out his ability to hold to that less than 10 millimeter settlement, 6 meters above the tunnel boring machine. And they wanted to see consistent control of the TBM. They also we were very interested in having them inject the bentonite into the shield perimeter to prevent the ground loss into the gap. And they had the equipment and capability of doing that, but they had not been doing it. And that was something that they then started to do. And we were most concerned because we were getting into sands and gravels where it was more critical to do that, to fill the gap, because we didn't think that we were going to be able to fill the gap just by the muck coming around the perimeter. And so this is what the measurement section looked like. And they ran the first tunnel boring machine through on the bottom part of that figure on the left side of the advance. And they were getting settlements that were pretty small and somewhat in the range of 4 or 5 millimeters, 2, 3, 4, 5 millimeters. And on the second drive, the contractor on himself, he decided that he would increase the pressures. They already were relatively high, but the overburden pressure of about 2.5 bars, and he operated that machine at a shield pressure of about 2.1 bars. As a result, the settlements dropped to less than 2 millimeters. The 2 millimeter was a kind of I've averaged out the data, but everything was slightly less than 2 millimeters or around 1 millimeter. And so you really had a situation where the only thing that is happening there is the elastic displacement around the shield due to the difference in that overburden and shield pressure. It's like a thick wall cylinder type equation. The displacement is proportional to the settlement. The settlement rather is proportional to the diameter of the tunnel boring machine times the difference in the pressures divided by a modulus. The consistent control is something that he really outdid it himself on that. The contractor outdid the control on the control of the pressures on the face. That's one of the most consistent records I've ever seen, with the upper face pressure at the bottom, the lower pressure, and then it increases then down to the upper part of the diagram, which is the lower face pressure. And that differential is you can evaluate that. The differential tells you that what the density of the muck is in the face. But the face pressures should, after you advance the 5 feet of advance, the face pressure should drop off towards the groundwater pressures. If they increase, it's an indicator that you haven't balanced the pressures at the face, and you probably have had groundwater flowing into the tunnel. But the consistent control was to maintain those pressures so that you never had them cycling up and down and reducing to the point that they would be less than the groundwater pressures. And the groundwater pressures can be dynamic here. They're going to increase above the static value. So having that distance of 1 bar between the upper face pressure and the static groundwater pressure supports the active forces, and it also takes care of any dynamic conditions. And so it was obvious that the contractor's performance was such that there was no question that he could tunnel beneath the Schulich building with under control. And he went and advanced under that building with 2 millimeters of heave and 1 millimeter of settlement. It was really a fantastic performance. And but it occurred because of the control that was occurring, and I think very much the consistency as well as filling the gaps. We go on now to the Alaskan Way viaduct, and that tunneling project has had a long history. That was a 2-year delay because of replacement of the main bearing. Had to put down a shaft and replace the main bearing in the area that was prior to going under the viaduct, essentially the contractor's yard. And so on April 29th in 2016, they exited the Safe Haven 3 and began their advance under the viaduct under Pioneer Square, buildings that are the late 1800, early 1900 buildings, and then under a large number of buildings in downtown Seattle. The ground there is once you get down below the tide flats and hydraulic fill and recent alluvium, it's basically heavily over-consolidated lacustrine clays and silts, the tills, outwash sand and gravel. And the key item here is that the outwash sand and gravel extended over the entire length of the project. And that meant that at the bottom of the tunnel, we were always in very permeable sands, and it had to balance the face to prevent that inflow into the face. If inflows occurred in those of that sand and gravel at the bottom of that tunnel boring machine, it could have caused voids that would move upward, but it would also cause softening and voids in the bottom, and that tunnel boring machine could go offline. And a 57.5-foot machine offline under downtown Seattle, but it's almost it's a tremendously difficult recovery, if not in some cases impossible. But the good news about that outwash sand and gravel is that because it was so permeable, the groundwater level throughout the entire tunnel was at about high tide level. And that meant that the pressures we had to balance for were relatively low when we got down to cover depths of 60 meters. It was relatively low pressure. And so here's the settlement criteria that was required of the project, and proposers on the project. I got involved here working with the proposer, and then also working with the contractor that won the job, and both the Washington DOT and the proposers and the contractors are trying to figure out how we can meet this settlement criterion of typically 1 inch settlement under most of the structures and half an inch under some of the Pioneer Square structures. And it was a major concern, and a lot of ideas put forward as to how to support all the structures, or a number of the structures at least, or how many do we need to support to prevent damage to them. And so one of the ways of estimating this is very commonly used in the industry in estimating settlement is to assume a percentage of volume loss, what the volume of the settlement trough at the surface, and take that value and apply it to a project, and use the experience from other projects. And so they came up with a 0.5%, 0.3%. We looked at people were looking at all sorts of different levels, and what it showed was that when you got down at shallow depth with a certain volume loss, you have a relatively narrow trench, settlement trench, and that means that you would then at that point have a larger settlement. And so you had a situation at each end of the line where the settlements were really very large. And so there's a series of mitigations that were considered. Micropiles between the foundations that went down within 15 feet of the top of the tunnel, and put in these micropiles between the existing foundations and the TBM in a close-spaced rows. They did that. The compensation grouting was planned, and by the time the compensation grouting was being prepared, we had the information from test sections that showed that our settlements were very small. And so the compensation grouting was eliminated. The grouting of the BNSF tunnel up to the BNSF tunnel, I'm not sure how that would have been done in any practical way. Those were eliminated. And then just giving a little preview of what did happen, the actual surface settlements, when we were at the shallower depths, usually less than about 100 feet or 30 meters, we really could not pick up the surface settlements. I think that we might have had settlements on the order of 1 millimeter at the surface. And in other places, you could pick it up a bit from the automatic total station measurements on the buildings. You could pick up some of that settlement when you sorted it out from just the normal tidal changes and other environmental effects that would cause changes at least as large as the measurements that we were trying to pick, the actual settlement that we were trying to pick up. And so the question is to you all, or to us as we look at this data after the fact, is why was that settlement so consistently small? And why does it, as compared to what these other estimates with percentage volume losses based on previous projects? Again, it's going to go back to the gaps as to, are we taking care of the gaps and preventing them from allowing flow into the gaps that would cause ground loss. The machine has a free air access into the spokes. Because it's so large, you can actually, workers can actually walk into into the spokes to change those rippers or that are right on the front of that tunnel boring machine, or in some cases they have disc cutters. They ended up on this project taking out the disc cutters and staying with the rippers. And then there's this chamber at the front, and that's what's pressurized with the conditioned muck. And there are 13 gauges on that face, which really in the back of that chamber that we call face pressure measurements, to measure the distribution of pressures and to ensure that the pressures exceed the groundwater pressures consistently throughout the entire project. And then that bentonite slurry is injected through the ports into the gap around the tunnel boring machine. And in that situation, you basically have on top 6 pressure gauges to measure those pressures and to ensure that those pressures are balancing the groundwater above, and they essentially will balance with the upper face pressures. There's a communication there. And so we start out from the safe haven under the viaduct, approaching the viaduct, going under the viaduct. After a 2-year delay and to replace the main bearing, the news was pretty much negative, but this was really the first positive news, that there are no adverse effects, no settlements. There was some heave because we pressurized in some cases almost up to the overburden pressure, but it's really like a pressure plate that we're advancing through the ground, and controlling that we can control settlement. We went on to into Pioneer Square, and the building that is circled. We were monitoring with the piezometers and extensometers. The contractor provided a report every 2 meters advance. To put out an email every 2 meters of advance. They would email information on all the settlements that had occurred in the vicinity of the machine and the pressures on the machine. We're looking at 2 things here. One is monitoring at the surface on structures, which is more or less to confirm that there are no impacts. You're not in that situation. You really aren't trying to use that to evaluate what's happening in real time with the machine. That's a little too remote for that. And so what we're doing is trying to monitor at the source with the extensometers and piezometers in order to find out just what is happening at those locations. And so and daily we'd have a construction monitoring task force, and they would meet in order to evaluate the data. The contractor and the owner's representatives would meet, and it really was having that coordinated effort is a key part of what is required, I think, to control and confirm that the ground control is being achieved on a project. Go on forward here. And as we approached one of the buildings, 1898 building, the piezometer there showed about 0.8 of a millimeter of settlement, extremely small. And then we got that undrained behavior where you get a little bit of drop off because pressures are dropping some over the shield. Even though you fill the shield gap, you get that drop due to the undrained behavior of the clay and the unloading. And the thing that was interesting then was, why is that settlement so small? What we see here is the overburden pressure is 4.8 bars. The upper face is 3.7 bar. And so that means that, and that's also on the perimeter. And so you have a very small differential. And so the elastic displacement is extremely small. We go on up the hill to the depth of about 60 meters, and we're beneath the Pike Street Market, fish market in Seattle, essentially directly beneath it. And the extensometer at that location is getting about 11 millimeters of settlement. Extensometer 74. Let's look at it. Upper face pressure and the shield pressure balance almost perfectly with each other, and that really is what you really want to see. You're supporting that top of that shield with that pressure. The face pressure drops a little bit. The piezometric pressure rather drops a little bit due to the undrained changes in the clay. And what we're seeing here is again, we as I said, 11 millimeters of settlement, much higher settlements than what we had when we were tunneling at shallower depths. And what is happening is that the upper face shield pressure is still about the same because there's not that much water to balance. I mean, we have that water at tide level, doesn't rise under the hill like it does in many soil profiles. And so the differential between the overburden and the upper face is very large. So when you just taking the relationship between pressure and displacement, you really can see that it was almost linear relationship between pressure and the displacements that we observed. It was really elastic behavior. As we look at these sands, I wanted to spend a minute on looking at what happened when we got on the sands in the crown. And in this case now, there's a sand there on the left side of the diagram, and you can see that as we approached, in this case, the piezometers are not showing undrained behavior. You're seeing flow. And so the piezometric pressure is building here as the TBM advances because of the pressures that you have in the fluids around the tunnel boring machine shield and in the face. And so what you want to be seeing here is that the upper face pressure is still maintained above the piezometric pressure sufficiently to balance the water pressure, its pressure. Well, that's happening, you can see that. But you also want it to be high enough so that it is also supporting the effective weight of material that's between, in this case, between your upper face pressure on the shield and the location of the piezometer, which is about 1.5 meters above the shield. And so here we have this 0.6 bar difference between the two, the dynamic pressure in the ground and the face pressure and shield pressure that are being applied. And so if you just look at that little zone there on the right, you have a differential pressure here of 0.6 bars. And then when you just calculate that 1.5 meters, the total weight of the water and soil in that interval will result in a pressure differential of about 0.3 bars. And so you're in a situation where the shield pressure is sufficient to have an outward gradient that is supporting both the water and the soil weight. And then even as the tunnel boring machine passes further, you get a cake forming, which gives you more of a membrane effect. And so you see the piezometric pressure dropping, even though the shield pressure is being maintained. And this is all over this zone is from the face of the tunnel boring machine to the tail. And so this is all over the tunnel boring machine. In this zone. It's all measurements that are made directly above the tunnel boring machine. I wanted to just show you what happened as we approached the BNSF railroad. And they were located about, I'm going to put it in feet, but about 24 meters, 80 some feet above our tunnel. And obviously, it was the main line of the BNSF. They're obviously very concerned about tunneling our tunnel and ground control. And so we had a series of meetings with them and a number of analyses WashDOT took the lead in terms of meeting with them and providing them with daily summaries. And I was working with the team, with the contractors team. We were preparing reports on these test sections that we had in at these various extensometers as we approached the BNSF tunnel. And so as we approached, the data that we're seeing there, and I go into that a little further perhaps, but it's really showing that we were 11 or 12 millimeters down at the tunnel would give us at that distance above the tunnel about 5 millimeters of settlement. And we estimated that would be probably the maximum that would occur at the BNSF. Some of the previous earlier numerical analyses using swimming more ground loss were coming up with things on the order of 15 millimeters. And even there, the settlements were not sufficient to be causing damage to the concrete lining of this early 1900 tunnel. So as we approach, the tunnels are at an angle here. As you can see the approach, our tunnel going down First Avenue, going north on First, and then the BNSF, we're going to be closest to it on the right side, and then it will pass it as the BNSF goes from our right to the left. And so what you will see here is the data that we were measuring with automatic total stations within the tunnel, and a series of lines along the existing BNSF tunnel, and even put some things on the ties, but mostly on the walls, what we were looking at. And those would be the most stable readings. And as we approached, we were about 2 diameters away. In other words, we're about 110 feet away at this point. And you can see a little bit of movement there, a very small amount of displacement. See that the displacement's picking up a little bit as we're now half a diameter away from the tunnel. So we're now within about 30 feet of passing beneath the tunnel. And then the cutter head is now under the tunnel, and we're still picking up more movement on the right because of the BNSF because of the angle that goes across above us. And as they got beyond, we're starting to get a much more symmetrical settlement profile. And the total was 5 millimeters. And essentially, the volumes I calculated for what was happening at the tunnel level were essentially exactly the same at the level of the BNSF tunnels. What impressed me was that we've seen this sort of data before, but you could almost say, you know, it was a typical data we've seen before where instead of millimeters, we're talking about inches. And so we really were impressed with the excellent precision that we have with such small settlements. As the TBM advanced out to the exit, the question was, will the injection and pressurization that we're doing support the sands as the depth decreases to 10 meters, and we have some clean sands in the crown? And so what happened in this whole section, and you can see 6th Street here where we're tunneling beneath it to the exit shaft, we really didn't pick up any significant surface or deep settlements. We could pick up a little bit of the deep settlement, but we couldn't pick up the surface movements, very much like what happened at the other end of the alignment. And so the question was, why was the settlement so small? Well, we started talking about that it's not ground loss that we're talking about. It's basically a more or less elastic response between the pressures and the displacements. And so this was the extensometer settlement just above the tunnel boring machine, which is very interesting. We had enough data. We had 150 extensometers, and we really got a tremendous profile here. And you can see at both ends of the project, there's almost no settlement directly above the tunnel boring machine, and then it increases up to as much as 20 millimeters when we were getting at the higher cover because of the higher stresses. And so just taking that differential pressure between the surface and the pressures in the funnel, typically on the order of 4 bars in the funnel, that was the distribution. Well, when you flip that and compare it to the surface settlement, you can see that they are basically proportional. And the relationship then there is basically just that elastic relationship. And we've taken some of this data and you just put a factor of K on that for some adjustment perhaps, but that E, you can determine that basically from the in situ data, and you're able to evaluate this for various projects. Well, when we in other locations where we're in soils, for example, which are not as stiff. And so this is kind of the approach that we've used over the years, the empirical data, and that 39-degree angle is what we use to estimate what the volumes would be in the distribution at the surface, and it came out pretty much as we expected. You can see that what we estimated prior to tunneling below the BNSF and what was actually seen. And there was another adit right at that location, giving us almost the same data with basically horizontal inclinometers or tilt beams. So excellent quality data that allowed us to evaluate both the numerical analyses and empirical relationships. And what I have here is a relationship using those angles based on empirical data as to how you can estimate settlement and the volume that is occurring due to the settlement, not due to ground loss. The other thing that we did, and some work that was done at University of Illinois by Professor Hashash and graduate students, Lou and others, they analyzed this just using Flax's 2D and 3D, and they used a hardening model, and they also just looked at it elastically. And what was interesting is that they basically baselined the stiffness from the in situ shear wave velocities from borehole suspension tests, and that gave some very useful results. Because it was really an independent, it was after the fact, but an independent estimate. It wasn't a curve fitting operation. And it was impressive as to how close that data came to what we saw with the actual measurements. There's a little bit, we typically see, even with a hardening model, that the distribution of settlement away from the tunnel tends to be a little bit different even with the hardening models compared to the actual data, which is why I still like to look at the empirical information and use in estimating settlement. It really confirmed there was no ground loss into the gaps, and using those shear wave velocities, and then using the G over G max relationship for shear strain, and you can see the shear strain levels. We are operating at pretty low shear strain levels, and so the stiffness of the ground is a lot higher than anything you can pick up, I think, in a laboratory test. And so the laboratory data really tends to be very difficult to use for evaluating stiffness, even triaxial tests. If you're really not making measurement that allow you to get a good undisturbed in situ modulus. And the shear wave velocities are obviously valuable for everything we've done with seismic work, but it's extremely valuable here as well for what we're finding of static behavior on underground excavation and tunneling. And this is what the pre-construction FLAC 3D analysis did. But what they did was assume, in many analyses, they assume a certain volume or volume loss, and they just added that in 0.35%. And so that is what, with the control that we have, we're able to prevent that sort of volume loss and use the relationships that are more like what we've been describing, the elastic sort of relationship. We had no ground loss. The shield gap was filled. The face pressures were maintained. It was one of the most consistent operations I've ever seen. Once they got through the problems, they started under downtown Seattle. It was just, they had a rhythm, and they really did a continuous support of that face 24/7 for 11 months and 5 days. These are some of the things that they're monitoring, the ground movements, the pressures, and then it's important to measure the pressures in the machine, not just looking at the geotechnical data of the ground. And that correlation is just essential, and it's something that we don't do well, I think, on projects where we have groups that are doing instrumentation and somebody else is doing the tunneling. That integration is extremely important. And this is that's in the exit shaft. And then we have had some work on the LA Metro. And it's interesting that we're getting the same sort of performance with the 6-meter tunnels where we are requiring the pressurization. And so we're using the horizontal vertical drilling more, doing that a lot for magnetometer surveys to locate abandoned oil wells, and also then using it for horizontal inclinometer, putting horizontal incliners in. And it's really, I think, changing the way we can monitor the ground, and we can extend these under buildings. And so we now have that HDD. And it was, we had the breakout and start of tunneling on regional connector project about five years ago now. This is just showing that that's horizontal inclinometer and SAA system. And as it progressed, as you start out, there's about 10 millimeters of settlement, which was due to the fact that you can't fully pressurize. But as you look at the face shield pressures above, the pressures are increasing as we continue to tunnel. We're getting deeper, but the pressure differential is reducing and the settlements are reducing. So I had, in these sands and gravels, had almost no settlement in at this location. We're doing this this is really things that we are doing now. We are requiring on Metro the filling and pressurization of all the gaps. Settlements are being controlled to values that are a couple tenths of an inch above the tunnel, and by the time both tunnels go by, they're less than 2/10 of an inch at normal depths. We're going under structures where we have to be controlling settlements to a couple tenths of an inch, even just half a diameter above the tunnel. We can use that means we've described for estimating, using both of course, the numerical methods are extremely useful, and using the right assumptions. The boundaries are basically pressure boundaries, are not displacement gaps. And then just one item here, I just wanted to point out that what we are starting to look at now is, and the Valley Transportation Agency down in San Jose is going to be driving a large diameter tunnels for putting the platforms in the tunnels. And years ago, we were talking, 10 years ago, we were talking about the fact that they're too deep. We couldn't do that because we had to have a diameter and a half of cover. At least that was the common conclusion. And what we're seeing now is with this control, we can be at shallower depths on the order of even half a diameter, but 3/4 of diameter, 1 diameter. That puts us at the right level for a transit system, where we're not much deeper. We can use the escalator. So it's a very major. I think it's going to be a major change in the future as we use more of these and eliminate the magnitude, eliminate the number of cut and cover structures we have to put in the street with our resulting impacts. So I think what we're seeing is we are achieving Brunel's objective. It's not that it has been achieved. It is present tense. You have to be doing the right things and controlling things to make it happen. But you can consistently do that in such a way that you can be confident on the project as an owner and dealing with third parties that could be impacted, that you can control that tunnel boring machine and prevent the damaging settlements. So open the ground in such a manner that no more earth shall be displaced than is to be contained within the shallower body of the tunnel. And those two little green dots there are people. And I think they're thanking the TBM, but I thank you all. I've enjoyed even remotely participating in this conference. Thank you.
Thank you very much, Professor Cording, for this wonderful lecture summarizing your vast experience in tunneling. I'm sure it'll be very useful to many engineers for years to come. We do have a certificate of appreciation that's signed by our department head and I will send you the certificate by mail. Again, I'm sure I speak on behalf of all attendees in thanking you for sharing with us this wealth of information. This concludes the Buchanan and Terzaghi lectures. We will upload the video recording and the booklet, including the speaker's slides, on the Buchanan website shortly. I wish everybody good health, and I will see you again soon.
Thank you, Jean-Louis.